Hey audience, I'm finally making some time to work on more projects, which is really exciting for me. It's been way too long. For all sorts of things that I want to build, I'll need to generate signals, like square clock signals for digital things, sine waves for testing audio circuits, and sawtooth and triangle waves can sometimes be useful when characterizing components with current versus voltage plots, stuff like that. So a signal generator that can generate arbitrary signals would be ideal. And an easy way to do that would be to use a microcontroller with an analog output. In software, we can make the voltage whatever we want it to be and have it change over time however we want as well. A simple way to do this is with a lookup table, or a LUT. It's basically a list of voltages, and at each time step we look up the next voltage and output it. The Arduino that I'll be using doesn't really have a built-in digital to analog converter, but it does have hardware to support pulse width modulation, or PWM, on some of its outputs. This rapidly turns a digital output on and off at a fixed frequency, but the percentage of a cycle for which the output is on versus off is adjustable by software. This lets us control the average voltage on the pin. With some filtering, we can smooth this out a bit and make it look more like the analog voltage that we want. This is really not the best way, or even a good way, to do this. The amount of filtering needed to really smooth out the PWM output would also filter the signal that we're trying to output from the signal generator. So this limits us to really slow, low-frequency signals. A better option would be to use an R2R ladder DAC, but the PWM method is easy and it'll get something up and running quickly. See, whenever I'm designing and building something, I run through a process of 1. Get something working at all, 2. Make it work well, 3. Make it easy to use, and right now we're only on step 1. A quick Google search shows that pins 5 and 6 for some reason have double the frequency for their PWM outputs, so we'll use one of those pins so we can get faster signals. The next step is to generate the lookup table. The analog write function in the Arduino, which sets the PWM duty cycle, takes a number from 0 to 255 as input. So what we want is to take a sine wave and shift its values from -1 to 1 up to 0 to 255. It would also be really convenient to split it up into 256 time steps. That way we could use a byte as an index into the list and just let it overflow back to 0 when we get to the end of the lookup table. I like to do this sort of thing with Python. Let's start with our time steps. We want 256 time steps, so let's say theta is equals something for x in range 256. We want x equals 0 to map to 0 radians, and we want x equals 256 to map to 2 pi radians. So we'll multiply x, the step number, by the number of radians per step. And we have 2 pi radians per 256 steps, and now we have a list of length 256 where the values range from 0 to just shy of 2 pi. Now we can generate the values using math.sine. So for each value in the list of these radian angles, we want to start by taking the sine of that angle. Now this value will be between -1 and 1, and we want to map those to integers between 0 and 255. So we'll start by adding 1 to make it all positive. So the range is now between 0 and 2 instead of -1 and 1. Now if we want 0 to map to 0 and we want 2 to map to 256, we can just multiply by 128. Then we round them to integers, and just to make sure that floating point rounding doesn't put us below 0 or above 255, let's bound it to 0 and 255. There might be a little bit of clipping, but that's not that big of a deal. Now all we need is a way to get this into our C++ Arduino program easily, so we can write a little function to output these lists as comma-separated hex values, which we can just copy and paste right into the Arduino IDE. So this works pretty well, and we can get a sine wave out of it. It's pretty rough because the pulses from the PWM output aren't filtered very well, but let's just not worry about that for now. This is fine. But what's not fine is that we can't adjust the frequency of the output signal. You could add a longer delay between each step for lower frequencies, but that means we can't go above the frequency we were at with a minimum delay. Once the delay is at its minimum, we can't step any faster. But one thing that we can do is make larger steps through our lookup table. For example, if we added 10 to our index variable each time instead of 1, then we could walk through our LUT 10 times faster, and the output frequency would go up by a factor of 10. It's going to be a choppier approximation of a sine wave because we're skipping a lot of values. Because of that, there will be a limit to how fast we can go this way, which I found is to be about 10 per time step before things start looking wonky. But this increase in frequency by a factor of 10 is pretty significant, so I'll take it. For lower frequencies, we can increase the delay per time step, but a far more versatile and interesting way to do it is to do the same thing that we did for high frequencies, but in the opposite direction. Instead of using an 8-bit number for representing our index into the table, we can use a 16-bit number, but only take the upper 8 bits when we actually index into the table. We've essentially split each of the entries in the LUT into 256 sub-steps. So if we add 1 to our index variable each cycle, it will take 256 cycles to step to the next LUT entry. Alternatively, our index variable can be thought of as a fixed point number now, where bit 8 represents the ones place, and bit 7 represents the halves place, bit 6 represents the quarters place, etc. So now we can make fractional steps through the LUT, stepping some integer number of 256ths of a time step each cycle. This also gives us a choppier sine wave, but again, this is fine as long as we don't push it too far. What we have now is kind of a special case of a fractional n frequency synthesizer. In a more general case, you could take a counter and add some number n to it each cycle. Whenever the count gets larger than some other number m, you make a step through the LUT and subtract m from the counter, leaving any remainder in place. If the rate at which you update the counter is your reference frequency, then the rate at which you make steps through the LUT will, on average, be n divided by m multiplied by your reference frequency. Notice how I said on average, though. If the counter value gets larger than m and you subtract m from it and have some value left over, that means you technically stepped a little bit too late. And if you have some residual value left over in the counter when you start counting again, you might step a little bit too early next time. The frequency will, on average, be what you expect, but some individual cycles through the LUT will be squished or stretched just a little bit. This adds what's called phase noise, where the frequency of your signal sometimes goes a little bit high or a little bit low, causing your signal to sometimes go out of phase with a theoretically perfect signal. I'm going to stick with this split into 256ths for now, instead of doing a more general fractional nth synthesizer, because this works using carries and overflows within my integer index variable, so I don't need any if statements checking the value of a counter and sometimes subtract a value and sometimes not. This is important because our software gets compiled down into instructions, each of which takes a certain amount of time to run. If the code sometimes subtracts m from the counter and sometimes doesn't, the amount of time spent during each loop might be different. Also, conditional branch instructions often take a different number of CPU cycles to execute, depending on whether or not the branch is actually taken. So even just having an if statement in something timing critical like this can be a source of glitches or phase noise. This doesn't actually matter for me since my signal is garbage anyway, and I don't really need precision for any of my projects, but sometimes I like to care about things that don't really matter so I can pretend that I'm doing real engineering. So now we have something up and running. The next step is to make it more usable. A knob to set the frequency, a button to switch between waveforms, a better DAC design. There's all sorts of stuff left to do here, so I'll pick that up in the next video. I'll see you then.